All right, today what we're going to do is we're going to be talking about points of inflection and concavity and how to identify this through analysis by using the first and second derivatives. Specifically using the second derivative to identify areas where a function is concave up, concave down, and then also seeing if there's any points of inflection. So here we go. First off, what we have is our example of our function f of x equals x cubed times x minus 4. And what we're asked to do is find any points of inflection and the intervals where a function is concave up and concave down. So what we're going to do is we first want to find where is this function going to be concave up, concave down. Well, concave up, if you recall, is when f prime is increasing. Concave down is when f prime is decreasing. So, in order to find this, we would actually want to test, all right, the first derivative and identify where it's increased and decreased. To do that, we're going to find the second derivative. And we're going to go through the process of finding the second derivative and setting that equal to 0. So, take that first function, f of x, and we're going to find the first derivative so we can find its critical points. So here we go. The derivative of f of x is going to be, if I simplify this first, x to the fourth minus 4x cubed f. So the first derivative is going to equal 4x cubed minus 12x squared. The second derivative is going to equal 12x squared minus 24x. All right, so we're going to take this derivative, and now we're going to set it equal to 0. From here, we're going to simplify this. All right, so we're going to take it and factor out a 12x. And what we have left over is x minus 2 equals 0. And so we have our critical points at x equaling 0 and 2. All right, so once we have that, now we're going to create our sign chart, just like we did with our previous functions when we found when f was increasing and decreasing. So using these critical points, create a sign chart with going from 0 to 2, so negative infinity to 0, going from 0 to 2, then 2 to infinity. Now we're going to test the second derivative. Taking the second derivative, we plug in -1 into here, and what we have is negative, and a negative makes it positive. Plug in a 1, and we get positive and a negative, which is a negative. Plug in a 3, and we get positive. So what we found out through this analysis is that on the interval from negative infinity to 0, we found that f prime is increasing, because f double prime is positive. We found that f prime is decreasing on this interval, and then it also then begins to increase again. Which then tells us, what about f? Well, if f prime is increasing, as we said up here, f is concave up. If f prime is decreasing, that means it's going to be concave down. And if f prime is once again increasing, it's going to be concave up again. So these are the 3 different intervals. We have up, then down, then up again. Now, we have points of inflection. Now, the points of inflection are going to be where f prime changes signs. So, where this changes signs. Now, where we look, we notice that, yes, f double prime changes signs at 0. So, yes, this is a point of inflection. And once again, 2 is also a point of inflection because, once again, it does change signs, and there's a value there. So, what's our point of inflection? Well, f of 0. Look at f. Where's our f function? Put it up here. You can see that. Plug it in there. We get 0. So, at 0, 0, we have a point of inflection. And then right here, at 2, when we plug it in, all right, 2 is going to be 16. And 16 minus 8 times 4, which is 32. And we have 16 minus 32, which is going to give us negative 16 right there. All right, and so we have that. So we have f of 2, negative 16, and f of 0, 0, all right, as a point of inflection. Now, if you look and graph this function, you can see that we have this graph, and this is what this one looks like. And I'm going to take this right here and move it down, extend this page a little bit, and let's look at our analysis and our graph. Well, if you look at this, we are saying from negative infinity to 0, and here's 0, that this graph is concave up. That means, if you recall, we have a little half smirk or a smiley face, and you see, yes, we do. All right, so that's when f prime is going to be increasing. We then see from 0 to 2, and this 2 being right here, okay, and 0 to 2, we see that it is going to be decreasing, so it's concave down. So right around here, and it hits this point, right, a point of inflection. All right, well, actually, 2 negative 16, so actually it'd be way farther down, because it's always at 10. So somewhere way down here, at negative 16, there is that point of inflection. I can't see it right now, but you can see that that right there is going to be concave, all right, down. And then once again, you see that we have it going up again. So what's happening is that this graph is going to be going up like so, and we have concave up. All right. So that is our graph analysis, and we see our 2 points of inflection. And at these different points right here, this can be 16. Obviously, it's not. But and also right here, we have. All right. Well, let's try one more. Take out the time on this. We have 6 points. All right. All right. So let's try one more. All right. This one, if you want to pause, you can and try it out, and we'll go through the answers. All right. But once again, we're going to try to find the points of inflection, and then we're going to find the intervals where the function is concave up, concave down. All right. So looking at this one, we're going to find, once again, the second derivative, because we want to first find out where f double prime equals 0. All right, so we're going to find the first derivative. I'm going to use the product rule. Take the derivative of the first, which is 1 times x plus 3 to the 1/2 plus 1/2 times x plus 3 to the negative 1/2 power times x. All right, we simplify this. We probably want to simplify this first. And what we have is x plus 3 1/2 plus x over 2 times the quantity x plus 3. And we can multiply both top and bottom by the square root of R2 times x plus 3. So we get a common denominator. And this is where all the fun algebra comes in. And what we have is 2 times the quantity x plus 3. Then we're going to have plus x. We have our common denominator, which is 2 square roots of x plus 3. All right. Simplify this. We should have 3x plus 3, sorry, not 3, 6, all over 2 times the square root of x plus 3. Okay. So that right there is f prime. All right. Moving a little farther. Okay, we're going to find now the second derivative of this. Okay, and I'm going to unhide my little thing. You can look at that, because I need a little bit more room. So, we have f double prime now. We find f double prime. We have the derivative, we're going to use the quotient rule, so the derivative of the top, which is 3. And times the bottom, which is going to be 2 times the quantity x plus 3. 1/2. All right, and that is going to be minus the derivative of the bottom, and so what we have then is x plus 3 to the negative 1/2 times top, which is 3x plus 6, all over the bottom square, which would be 4 times x plus 3. Okay. From here, we can look at this graph, and we can try to identify some possible points of inflection where this equals 0 or this is going to be undefined. And what we notice here is we need to simplify this a little bit. And we have 6 and the square root of x plus 3 in the numerator. We then also have minus 3 times x plus 6, that quantity, all of the square root of x plus 3. And all of this is going to be multiplied by 1 over 4 times x plus 3. Big bad algebra problem. This is a nasty one, buddy. Okay. Pause this. Been a lot of people that have been interrupting me while I'm doing this. So yeah, laugh about this. So let's see if we can simplify this now. All right, we get a common denominator, so we're going to have multiply top and bottom by square root of x plus 3 and the square root of x plus 3. And we're multiplying just this side right here. And we have 6 times x plus 3, minus 3x minus 6, all over the square root of x plus 3. And this right here, my friends, is all multiplied by 1 over 4 times x plus 3. Oh, wow. All this work for just one problem. Whew. Should not have picked them, don't I? We got 6x plus 18. And we have minus 3x, and we have minus 6 all over the square root of x plus 3. And then all that multiplied by that expression. Whoops, hello. All right, so we have this 1 over 4 times x plus 3. Okay. Simplifying this a little bit, and what do we have? We have 3x. This right here is going to give us plus 12. And we have the square root of x plus 3. And that's going to be multiplied by the quantity 4 times x plus 3. All right. So that is f prime, double prime. From here, we want to set this equal to 0. And we notice that we can have x equaling -4 on top. All right, and we also notice that looking at the denominator, so when it does f double prime, when does that not exist? And we look at the denominator for that, so right here, and we realize that x equaling -3 is another point. Okay, so from here, we're going to test this out to find out what is happening with this function. So we do our sign chart now, and looking at our derivative. And we have -4. We have -3. We're going from -3 to -4. We're going from -4 to -3. And also -3 to infinity. And we check out our f double prime. So when we test out f double prime, we plug in, first off, -5. -5, we get a negative on top. But -5, notice when we plug it in here, we get a negative inside the square root. That makes it no good. So this does not exist on the interval, which is disheartening. So then we plug in another value. So let's plug in, I don't know, -3.5, because that's between those two. -3.5. But once again, we see that we'll probably get a negative on top. But here, once again, it does not work when we plug it into our square root. So this one doesn't work. So now we go and we plug in, okay, let's plug in 0. 0 is pretty easy. Positive, plug it in the bottom, it's positive. Positive, positive, it's positive. So we know that f prime is increasing on this interval. We know that f is going to be concave up. And we have that. Wow. All that work for one interval, -3 to infinity, being concave up. Points of inflection? Well, possibly here and here, but we notice that there is no sign change, so there is no point of inflection. No point of inflection, so no points of inflection. All right, no point of inflection. Point of inflection here. Well, let's verify this by looking at our graph. I have this graph way up here, and I'm going to bring it down. Follow along with it. Hey, there it goes. All right, and if I take this graph and we compare it to our analysis, we notice that at -3, our graph starts here. And it looks where that could be possibly a point of inflection. But it starts here and then all of a sudden goes up. And you notice that it is concave up throughout that little hook. And that's what our graph is. And that's what we found. So we did our graph analysis. Okay. So those are 2 examples on how to analyze for concavity. All right. Concave up, concave down. We're looking for when f prime is increasing or decreasing. And we do that by first finding the second derivative, setting it equal to 0, and finding out where it doesn't exist. Those would be our critical points for our first derivative graph. and then we test them by using a sign chart and to determine if f prime is increasing or decreasing by finding the signs of f double prime. All right. Well, with that, here is your homework assignment. All right, I would ask you to do all of these. Would you please justify your answers? Or actually, no, you don't have to justify your answers. There it is. Enjoy. Good luck. Make sure you do and show all your work. So we'll talk to you later.